So hello and welcome back. Let's do lecture 9.1 example 3 on power factor correction. Find the value of a parallel capacitance needed to correct a load of 140 kVAR at 0.85 lagging power factor to unity. Assume the load is supplied at 120 volts RMS on a 60 Hertz line. Make sure to draw the circuit, power triangle, and phasor diagram before and after power factor correction. So first we'll draw the circuit. So we're going to have a circuit here where the source value is 120 volts RMS at 60 Hertz. We model our inductive load as a resistor in series with an inductor. And so that combined has 140 kVAR and 0.85 power factor lagging. And then our goal is to find the value of a capacitor to put in parallel with it so that it now has a power factor equal to 1. So that's our goal, is to find that capacitor. So looking at the original system, we're going to have this power triangle here where this is 140 kVAR and the value of this angle theta is the arc cosine of 0.85. The arc cosine of 0.85 is 31.79 degrees. So now I can find P and Q for the original system by using 140K times the cosine of theta, and Q is equal to 140K times the sine of theta. So P is equal to 225.9 kilowatts. And we need this to be the same P when we're all done. Remember, P does not change. And Q is equal to So next we're going to draw our power triangle. So here we have our power triangle, where we have on the power triangle that Q is equal to 140 kVAR, and we need to find this angle theta. So theta equals the arc cosine of 0.85. So theta is equal to 31.79 degrees. So next we're going to find S. So S is going to equal P over the cosine of theta. P over the cosine of theta is equal to 265.76 kVA. 265.76 kVA. And P, what are you doing? You are just acting up now. So P is going to equal Q times the tangent of theta. Q times the tangent of theta is equal to 225. I must be getting tired. That's all I can figure. Q over P. P equals Q over the tangent of theta. So P is equal to 225.9 kilowatts. Remember, this is the same value we should have when we get to the end. 225.9 kilowatts. And S is going to equal P over the cosine of theta. S is equal to P over the cosine of theta, which is 265.76 kVA. So now we have completely modeled our system. So the next thing we want to do is to find the values for the new power factor. So we know that PF new is going to equal 1. So theta new is going to equal the arc cosine of 1, which equals 0 degrees. So something interesting happens here. And what we'll see here is that P is equal to S new times the cosine of theta. So by doing that, you are going to get that since P was equal to 225.9 kilowatts, S new has to equal 225.9 kVA. And with this unity power factor, this is as efficient as you can get. Q new will equal 0 bar. So now when we solve for QC, QC is equal to Q minus Q new. So we see that the capacitor has to cancel out all of that Q value. So the capacitor has to equal 140 kVAR as the reactive power. So now C is going to equal QC over omega VRMS squared. And we are given all these values now. So we have 140K over 2 pi 60 times 110 squared. And so we are going to need our capacitor to be 30.69 millifarads. And so that's what we're going to put here, 30.69 millifarads. And we're going to get the model for the current through the capacitor, the current through the load, and then the current for the source, where we know that the current from the source has to equal IL plus IC. Okay, and so now what this is going to look like is, unlike last time, now when you add that capacitor on, you're going to see QC is going to drop that imaginary part all the way down to 0, so that afterwards there's not really a triangle anymore. You're just going to have 225.9 kilowatts, and that's also 225.9 kVA, like that. So there is no triangle anymore because the capacitor subtracts all that off to a flat line to get that angle of 0 degrees. So let's take a look at what our phasor diagram looks like. So let's do all of our calculations first. So the current through the capacitor is V over the impedance of the capacitor. So it's going to be 110 over 1 over J times 2 pi 60 times 30.69 millifarads. So the current through the capacitor is 1272 with an angle of 90 degrees. Okay, the current through the load is going to equal S over V conjugate. Remember, this is our original S. So this is going to be 2416 with an angle of negative 31.79 degrees. And the current from the source, you can either do S new over V conjugate, or you can do IL plus IC, and that's going to be 2053 with an angle of 0 degrees. 0 makes sense for a power factor of 1, and negative 31.79 makes sense for the power factor of 0.85. So now we're going to have our imaginary axis here. We're going to have our real axis here. And we're going to have IL down here with a magnitude of 2416 and an angle of negative 31.79 degrees. And then when we add on the capacitor, what you'll see is the capacitor actually goes all the way up to the real axis this time with a value of 1272 and an angle of 90 degrees. That's IC. And so then what you're going to have is, when you sum those together, you're going to have the current right here on this line. And that's now going to be IS, which is just 2053 with an angle of 0 degrees. All right, we have one more example in this lecture, so please come back for the last one.